Um, Hi, everyone. Hopefully you can hear me with my mask. I'm a little bit sick today. But I'm very happy to introduce Debbie Leung from the CMO department in the IQC to give the Tutte Colloquia this week.
Thanks, Sam, for the introduction, and I'm very happy to be here to give the colloquium because it involves a lot of people who have connection with the department. This work actually started more than 10 years ago. For those who have been here for long enough, Andrew Childs used to be a faculty member here until about 10 years ago. And the work indeed started when we share a master's student, Hong Kong who recently, so he recently went to Concordia as a faculty member. So that was a while back. And we have other collaborators. Then is an intern with Andrew before the rest of us joined the project. On Maris, a lot of you may remember him too. He was a PhD student here with Andrew and I. And Maris actually graduated before Hong Kong started working with us. But Maris was visiting Andrew at the time when we were working on it, when Andrew left and went to UND. So we also ended up participating in the project. And then we have a new collaborator very recently, Shini from the Perimeter Institute. Proceed. So the common state purification problem is an information processing problem. So which means I should define what the problem is and list the prior work, what are the solutions before our work, and show the algorithm that we have to solve it. And we should analyze the performance. Of course, I should also explain to you why we care about this problem. So I should mention some applications for the quantum state purification problem. And then what we're doing since the submission of the revision of the archive paper in July. But I realize that this may be the first quantum talk for this term. And we may have incoming students who have not even seen the first quantum colloquium. So I should take a few minutes to say a few words, what you need in quantum mechanics to see the talk. And apologies to the people from IQC, you probably know about this well enough. But this is a physics slide. Just like your hard disk or your USB drive, there are quantum systems that you can consider as medium or a storage space that you can use it to hold quantum data. And some example, when I was a PhD student, I worked on nuclear spin resonance implementation for quantum computation. And so in that case, the spin has two states that can be distinguishable, that can be distinguished from one another unambiguously. It's spin up and spin down. Meanwhile, we may have heard that light waves has a particle aspect, so we call these photons. In the photonic mode, there are distinguishable states labeled by the number of photons inside. So in the second example, the distinguishable states is corresponding to essentially at the moment to be seven non-negative integers. So then you can abstract to what would describe quantum data. Mathematically, these are D by D, positive semi-definite operators. So just matrices that has non-negative eigenvalues. If they have to be trace one, forgot to write it on the board. And the distinguishable state are the labels for the basis for that long space that we associate with the quantum system. So if the quantum system has D distinguishable state, we associate to this space a D-dimensional long space. When we have multiple systems, then we take tensor product of those non spaces, so the dimension multiply. And this is an example of the quantum state, and this is in fact the most of the quantum state you need to look at for this talk. There are two. So there are two. Delta is a real number between 0 and 1. So you should, and then these two states, these symbols inside the circle, each of them is a quantum state. Quantum data is much more quantum state. The one on the with the green circle. So you should think about it as a complex combination of two matrices, each of them represent a quantum state. You can also think about it as mixing up two states, one with probability delta, the other one with probability 1 minus delta. The state with the green circle earlier is the identity matrix, so it's positive and definite in the straight one. It represents the fact that you have a completely uniform mixture over all the computational basis state, the basis states. Sometimes you call it computational basis state. The state in the red circle is a projectile onto a one-dimensional subspace spanned by the vector. So we write a vector like we call it a cat with this symbol. We label the state by side, but then we use a bracket, which is a straight line and a right angle, to represent the vector. We call it a cat. The dual of this vector, we write the other angle. We use a left angle, the symbol of the state, and then a straight line. And it's called a bracket. It's the bracket notation in quantum mechanics. But what you need to realize is just that it is a projectile one-dimensional space there. So this state represents mixing up a rank 1 state with a completely uniform mixed state. The pure state side, the rank 1 state is called a pure state. It's just a convention. It's opposed to a complex combination of state that we call a mixed state. You mix them up. Then in this problem, so there is another piece of quantum mechanics that I should mention. If I prepare the state, I give it to you. You're holding that system. You are not necessarily knowing the description of the state that you're holding. Think about the vector representing the rank 1 state, and you have coefficients in front of the basis state. Having a copy of that state in your hand does not allow you to learn about those coefficients. That's just a fact from quantum mechanics that I would need to mention. And so you should consider the fact that the rank 1 state is a pure signal state, but you don't know what that signal is. You want to do something with it, you want to learn something about it, but you're not knowing it upfront. And the other term, the algorithm term, has nothing to do with the signal. So this represents noise. And in this state there, the noise probability is delta. And the signal is 1 minus delta term. So you get the signal with probability 1 minus delta. So then the problem to purify the state is to take that noisy state and to want to output a copy that has noise probability epsilon. For epsilon much smaller than delta. You want ideally epsilon to be smaller than anything that you need to worry about. Except it is not allowed. It's not possible in quantum mechanics. This transformation will break a lot of rules, such as you can distinguish what is that signal state better than you can with the original state. So the solution to the problem is to have more copies of original noisy state to offset the fact that you end up increasing the distinguishability, because now you start with more number of copies. Now, these more number of copies have to be paid for, either by preparing the state more time, so it takes more time and work, or you have to pay for it in some, you have to buy it from a vendor or something. So N represents the cost, one cost of the purification problem. It's called the sample complexity because you can think of having N copies as having N samples of the noisy state. Then there are questions that you can ask. So one thing you can try is to minimize the number of copies of the noisy state that you need to perform the purification problem. Later on in the talk, we will see that we also want to minimize the actual circuit that will allow us to perform the purification. And so let me mention a little prior work on the number of samples. In 98, for the case when the dimension is 2, so each state is 2 dimension, and then you allow many copies and copies. The complexity has been shown to be asymptotically optimal in the sense that when n is large, that O 1 over n is not important. Then roughly speaking, you need 1 over 2 epsilon and then over 1 minus delta square. So it is inversely proportional to the final error that you want to achieve. The very general function of epsilon. For a long time when we were working on this, we assumed that the initial error is a fixed number. We thought it's not a very important parameter, so we just assume that it is a fixed parameter. But later on, we will consider the case that delta will approach 1, which means that we have increasingly small amounts of signal. So they prove that this is optimal, and they have a protocol to do that, to do the purification. And furthermore, there is a very curious side bonus of that protocol that they have. Instead of producing just one copy, if you want to produce n times 1 minus delta of the copies, as long as you don't use those copies jointly, it doesn't affect the fidelity, it doesn't affect the noise rate. Very similar timing by Carol and Werner. They studied the same problem. They studied more error definition and so on and so forth. So I just want to mention that there is a second paper on the same subject around the same time. And when Hong was here as a master student, we solved and we proved a very similar result for 3 dimensions. And instead of 1 over 2, we get 1 over 3. The algorithm is also a very natural generalization of the one considered by Zero Alpha and Machiavelli. It's based on what we call mixture sampling. It's just measuring how much symmetry your system has, and use that information to reduce the dimension of the input. In previous version of this talk, as recent as 2 to 3 weeks ago, I mentioned that we were basically stuck on evaluating the fidelity for larger dimensions. And so instead of trying to bang our head on it, we decided to consider a different algorithm. Last week, Hao finally finished his thesis. Along with other people that are also connected to me. This Lee is not Shirley, that is Xiaoyu Lee. He was an intern here 2 years ago, and he went to MIT to work with Aiku was my teacher. And then there was a fourth one as a goer. They solved the problem essentially, and the result is exactly what we expect. The algorithm was what we suspected to be the optimal algorithm. The evaluation was done, and it's D minus 1, but he got the test in his thesis. So it was really nice because now finally we have something to compare with. What we have done instead, there is another direction that has been done in the literature that this result concerns fair probabilistic distillation, but we want to look at the approach in which we must produce the output, but we want to understand the expected number of copies needed. So instead, when you look at an algorithm that is pretty natural, it is not even much to invent the algorithm. It is a natural way to just do things and see how well it works. We do not need to optimize the sample complexity. It turns out to be very optimal for medium to low noise. The advantage why we look at it is because it's first of all the sample complexity is good enough for the purpose that we have in mind, the application that we have in mind. But most importantly, it also has efficient circuits. We have a word on the circuit size for the procedure, and very low quantum memory required in one of the architecture called the stack implementation. And finally, it is relatively easy to analyze that we have understanding of this protocol well before the analysis that talks about the optimal protocol. The optimal protocol, let me mention that despite the fact that we have this expression here, mixture sampling require a fairly large circuit, a large quantum circuit perform. So there is some issue using the optimal method to do purification. It will require quite substantial quantum computation resources. Not in terms of the number of copies, but you need a very large size circuit and a lot of gates and perform the purification for much longer time. So the algorithm consists of has only one basic component. It's called the swap test. What it does is to take two systems, S1 and S2, d-dimensional each. And so the input is an arbitrary d squared by d squared matrix. This is the size of the input. The circuit for the swap test is in blue. The first step is to attach a rank 1 state. I just write it back here instead of writing the jacket in full. We call it the plus state. It's just the state that has 1 over square root 2 in front of the two basis centers. So the first register is 2-dimensional. I'll say what is a gate in the middle in the next slide. The last step is a measurement on this state that we attach. It is a measurement what we call along a basis, but what it means is that we project the state. Now, to track the size of the system there, we now have the actual system with the 3 register has 2d squared dimensions. And then with the measurement, we project it down to 2 possible d squared. Not necessarily in that block. I did not label the basis there. But the measurement will project it down to 1 out of 2 possible d squared dimensions of space. And the gate in the middle is called the control swap. If the state of the first register is in the 1 state, then we swap S1 and S2. That's what it means. And so if you have d being 2 to the k, you can decompose that control swap into k such control swap. You just swap each of the you can think about d being 2 to the k as having k 2-dimensional systems. And then you do the control swap of these 2-dimensional systems one by one, and then you do k times. So the surface size for this swap test is actually log the dimension of the system on that order. It's a very small concept that I did not bother writing down. Depending on the outcome, you may have projected the input onto the symmetrics of space or the anti-symmetrics of space. Correspondingly, we see that the measurement outcome is plus or minus. If the input is uncorrelated, which means that we have a state on S1 rho and a state sigma on S2, then the probability to get a plus outcome is having bias trace of rho times sigma. Now this is only close to 1 if both rho and sigma are close to being pure. It should be close to being 1, and they should be very similar to one another for that to happen. So the intuition is that if we already get a plus outcome, maybe the state that, despite the fact that it has a certain description before the measurement, we may have selected an input that are more similar to one another. And that's the intuition to say that the protocol itself is to take 2 copies of the same state, so now sigma is also equal to 0. Now we have both rho and sigma included. 1 copy of each system. Then, if the outcome is plus, then you throw away 1 out of the 2 systems. Let's say that we throw away S2. The remaining state in S1 has a very simple form. Is at the same eigenvalue position, just different eigenvalues. If you just check what happens to the maximum eigenvalue, and if it is non-degenerate, which means that the second largest eigenvalue is just smaller than that, then the output will have maximum eigenvalue larger than before on the same state, on the same eigenstate. So that would have performed the part of purifying the state a little bit. You push that weight of the desirable signal state a little higher. And the idea is to recursively run this protocol. You take 2 copies. If the outcome is plus, then you keep 1 out of the 2 systems. Then you take 2 more copies. In this case, my outcome is minus, so I throw everything away, can't be used. Then I ask for 2 more copies. Now this time I get the plus outcome. So now I have 2 of these outcomes that are slightly more purified than before. I will take them through another swap test. This time I get another plus, so I keep one out of the two states. And then I'll ask for more copies so that I have another state, which is the same noise level as the one that I prepared earlier. And I try to bring them to yet another swap test. If the outcome is minus, then everything get wasted, I throw them all away. And I repeat the protocol. So then we should define at every level of the iteration, what is the noise rate. We start with noise delta, call it delta 0. After one round of the swap test, the noise will go down. We call it delta 1. If two of these delta 1 noise they get swapped tested and get a positive or outcome, then I call that noise at that second level delta 2 and so on. So we stop the protocol when delta n is smaller than or equal to epsilon, and then output the same. This looks ridiculously inefficient. It is very simple. The idea is very simple, and we pay the price by doing a lot more work. But things start to be a little less unexpected when we count how much memory we actually need. In the step-based model, it happened that we only need n plus 1 three-dimensional system to perform this purification. We call this a streaming model. We assume that you don't need to store all these samples at once. You ask 2 of them at a time, you ask another 2 at a time. You don't store them, you ask. And you only need to store the one that you just asked. The step-based model, if you look at the Wikipedia, it said that it's named after a stack of plates. And some of them. And what you're allowed to do is to write over the bottom one. You can write something over the bottom one. You can also take the state of one plate and write it to the plate on top of it. And so on. So you can always push the state to the data one level up. So if you have a static model like this, an architecture like this, you can ask for one copy of the noisy state, then you can push the noisy state up. You can ask for a second copy, then you can perform the swap test on these two registers. If it is good, you keep this copy, let this be overview the data. You push that one up, and then you ask for another 2 copies here. And if it is good, then you have go that one here. You can always swap test here. If it is good, push it up. If you keep doing it, you never need more than n plus 1 of those registers. It turns out. But it's very space efficient. And then the next thing to ask is then how many samples do we need and how many gates do we need to perform this? It is really obviously exponential in the number of equations. The sample complexity is at least exponential in n, and the number of swap tests is the non-lead registers, and that is roughly speaking the same as the so that is also exponential in n. So what we want is to ask how many iterations will we need to purify the state? How quickly can we suppress the noise? Then just go and write down the recurrence. If you have input noise delta I, then what is the output noise delta I plus 1? It's not hard to write this down. So what I want to say is that there are 2 features on the recurrence. The first is that when the dimension is large, then these 2 terms basically disappear. And it becomes more or less independent of the dimension. It is a little unexpected. You think the larger the dimension, the more work it takes, maybe the performance will go worse. But after a while, increasing dimension has something very big difference in the conversion to the noise. The second interesting thing is if the noise is sufficiently small, you drop these 2 terms, then every time you repeat this stop test, you suppress the noise by a factor which is this quantity here. If that one is pretty small, then this is basically 2. Even if it's not 2, it's a number which is quite far away from 1. So you reduce the noise by a constant factor every iteration, which says that essentially you know that you will have exponential conversions of the noise to 0. One other thing we need to worry about is when we get the minus outcome, we have to throw things away. So we don't want that to happen. So at what probability we get the outcome that we want? This is the equation for that probability. And once again, no matter when the noise is low enough, you don't really think about the time. And what we're speaking, it is just learning the time. And no matter what, it's never smaller than a half, which is important. But when that is not, then it becomes very close to 1 itself. And it is easier to just look at the plot. The work is analytic, but it is much easier to just talk about the plot. So this is very representative of the behavior. Here we have 95% error, only 1% signal. And this is the noise suppression as the number of iteration of the process with different dimensions. And you can see that the dimension does not matter so much after a while. The red line being equal to infinity is a limit that we take to allow us to bound the performance, because that's the worst case scenario that we can prove. There are 3 regions of these plots. These gray lines can be set anywhere within some wiggle. I have chosen some values here that does not correspond to what I said, because we have changed where these thresholds are a little bit throughout the project. Suppose I set this at 2/3 and 1/3. The worst case scenario is that it takes about 3 to 5 iterations from 2/3 noise to 1/3 noise. Then below half, but if you want to be very safe, completely below 1/3, the noise is exponentially increasing, as advertised earlier. The troublesome one is actually the very high noise reading. It's very flat, especially if the dimension is large. But it turns out that we can prove that it will hit the point to the 2/3 roughly after 1/delta plus, I didn't say here, is 2 log 1/1 minus delta. That number of iteration will push the error to 2/3 from delta. Then if you start from here, the noise is here and here is 100, then you multiply the sample from here to here, and multiply the number of samples from 2/3 to 1/3, and then from 1/3 down to this one that you want. We multiply all them together. So let's see what is a nice part of the result. When the noise is no more than half, then delta I is never bigger than, if the initial delta is no more than 1/3, then delta I is no more than 2 to the power minus I. And so you need only log 1/epsilon iterations. Then you can count the sample complexity by noticing that for every test, you take 2 copies. You need to repeat it the expected number of times 1/pi. This is 1 iteration. You multiply that according to all iterations together to get the actual sample complexity. But surprisingly still, you raise 2 to the power log 2 1/epsilon, you get back 1/epsilon. You multiply all the 1/pi together, because the pi converges to 1 so quickly, it is actually 1/1 minus 2 delta. If you compare that complexity with the optimal complexity, previously we can only compare to 2/2, but now we can compare to any dimension. These behavior are very similar up to a small constant if delta is not too close to half. So up to half noise, the very naive, almost wasteful slope test is almost sample optimal. And you save a lot of memory and circuit size and so on. The circuit complexity, remember that the number of slope tests is the number of leaves, so it's not bigger than the non-leaf vertices, so it's never bigger than the number of leaves. So we can take the sample complexity, multiply to the number of gates per slope test, and get the circuit complexity. And this is the polymetric that we need, and so everything is good for low noise. Any question? If it is medium noise, then we have to perform the purification from 1/3 to 2/3. The upper bound on how big a multiplicative factor you incur is 2 to the 10. Is multiplicative. If you do the calculation more carefully, for fairly moderate dimension, this is much smaller than 2 to the 10, but 2 to the 10 is the worst case scenario. So if you go to the really noisy regime, that's a different problem. I won't say how to do this. This is actually not so easy to do. But it's popular good. It is a straight up or down, and it is also tight. The asymptotic result is exactly that expression, and it's also proved to be an upper bound. It was true for the largest, I mentioned the worst case scenario. If your dimension is smaller, you can get a side effect. Which give us these two results, that if we have very large dimension times zero, then the expected sample complexity is exponentially more over 1 minus times this factor that has the middle noise here and the low noise here, the one of these two numbers together. If instead 1 times 1 minus 7, b times 1 minus 7 is very small, much smaller than 1, and b is moderate, then the expected sample, number of samples is this number that is, if this is much smaller than 1, then 1 over 3, 1 minus 7, this is the number greater than 1. You raise to the power which becomes quite big, it is probably when b is large, but for small b than 1, the exponent is 4.8, 6.2, and so on, and then it gradually increases. So the very high noise in a very high noise regime, the behavior is not so, the performance is not so good, the recursive is so fast. Before the result from last week, there is only one other protocol I can compare with on the very high noise regime. It is not known to be optimal, and in fact, we think it is not. And it is the method to actually try to use many copies of the quantum state to learn about the coefficients, every coefficient of the matrix. You just want to learn everything about the state, and then you go and prepare the pure state component that you have learned. If you use this method, you will have a sample complexity, which is 1 minus delta to the power 1, x to the power 2, the way we want to do it. And the dimension of the power is 1 or 2, depending on whether you want to use the string method. If you use the string method, it has to be power 2. But if you allow some collective measurement between different properties of the power 2. And then the second one, harder. Tomography is actually a fairly quantumly, it is a very short circuit. You just make measurements on the state, and then you classically join these measurement outcomes together to compute what the state is. So our method has two 1 minus dependence. Tomography has very dependence on 1 minus delta, but it has dimension dependence as well. If you do tomography, after you learn what the state is, you have to go and prepare the state. In the swab test method, we don't need to. It's just sitting there. So if the state is very hard to prepare, then tomography also causes you a little problem later. So let me tell you what triggered this research. Andrew worked on algorithm, and I work on quantum information, so it is a little strange that we work together on this. He has a computational problem in mind that requires purification. Simon's algorithm is the third quantum algorithm we will learn in either 481 or 681. But in short, it is a query complexity problem that is an oracle, and the oracle will increase an n-bit string in your signal state. You want to learn what that n-bit string is. And Odette asked this question: what if my state has some noise now? it has this I over 2 to the n naught. Will I still have the same quantum advantage, or I lose most of the quantum advantage? At the time, he thought we would lose the quantum advantage. He tried a few methods to overcome that noise. Andrew's idea is that let's purify the state first, and then perform the original Simon's algorithm on the less noisy state and hope for the best. So it turns out that for delta, you can use roughly speaking 3 over epsilon copies of the noisy state. You get 1 copy of the rho epsilon, and take epsilon to be 1 over n. Then we will have to perform all the n squared queries instead of all the n queries for Simon's algorithm. But we at least retain the polynomial size second and the number of queries that we need. So we restore the quantum advantage from exponential to polynomial for this particular problem. And I think this is the main motivation we have at the time. There is a second application that I found recently because I want to compare our method with tomography. And so I look at John Wright's thesis. There is a problem that is called mixedness testing. So the game is that there is an unknown state rho, and then you can ask for n copies. The goal is that you have to determine whether rho is the maximum mixed state given by I over d, or it is epsilon far from it in the trace system. He showed that it required d over epsilon samples in general. If rho, we have no promise on rho. What we show here is that if rho is of the form that we wrote down, but we don't really know the noise parameter, then one solution to play this game is that we can try to purify the noisy state. If it is I over d, you never get any purification. There's nothing, there's no signal in I over d. If there is a small state, pure state component, then you can just try to purify that pure state component enough number of times. After you have done the attempted purification, you compare, do I still have the maximum mixed state or do I have the pure state? That is actually very easy to perform fundamentally to distinguish these two scenarios. So remember that our protocol is dimension independent. The sample size can be made dimension independent. So at least we know that if we restrict the interstate for this mixedness testing problem, the dimension dependent will appear. So the problem has less complexity for restricted set of state, which Angie told me is not surprising, but at least we know that certain restriction will reduce the complexity of the problem. Finally, purification in 2 dimensions is similar to a problem called the quantum majority problem. You imagine having a bunch of bits that is in a basis that you don't know about. Then you want to perform the majority voting in that unknown basis. Yes?
Sorry, could you go back to the previous slide? So there where you're saying purifiable rho, does that mean it has just a rank 1 matrix added with some small coefficient to identity?
I'll tell you what that is. It is any state that has maximum eigenvalue bigger than the second largest eigenvalue. The difference is the parameter that we got.
Constant difference.
Yes. So it turns out that for 2 dimensions, the majority problem and the purification problem are essentially equivalent. If you have n qubits, you can permute them around and then you can do the purification, and the output will be effectively the majority. If you can perform the majority, you can use it to purify the state, vice versa. So our protocol and other protocol for purification provide the generalization of the quantum majority problem for D dimension. Finally, purification is a natural reverse of cloning. In purification, you take a large number of copies of noisy state and you want a smaller, pure number of copies. Cloning takes a small number of copies of good state and dilute it to a larger number of noisier state. So these are reverses of one another. The original method by Syria, Eckhart, and Machiavello, and the one by Kell and Werner are reversible. So when they purify, they also learn how to form. Our method is not. That is a little unfortunate. One extension of our work, one visual, is to think a little bit about whether there is a way to break this lack of connection with forming. And finally, I mentioned some extensions to what I mentioned. We constantly change the analysis to hope to save a few more samples. We're a little shocked by the fact that we're not as competitive with the high noise regime. So there are slightly different ways you can perform the swab test. The one that doesn't work, upfront, is to take more copies and perform a cyclic shift on many copies. The probability to pass is actually too low. The ones that we know that works, but does not provide as big an improvement in the error suppression, is when we perform the swab test, we throw one copy away when we get the pass outcome. We don't need to. All you need to do is to make sure that the two copies that go out from one swab test never get in touch with one another again in the future. And if you know how to make sure that you track where they are, etc., and you're willing to put in more quantum memory, then you can use both copies, but you have to track whether they accidentally went into the same swab test later on or not. If they do that, break some of the capabilities and it will not work. But you can potentially use both copies. The other fun one is that if the swab test fails, if you give a minus sign, you can take the copy and you can take two bad copies. You can again try to purify. With something that we did not expect, but for error, which is kind of bad, but also bad to mind, we find that actually just failing use two iterations. So it's not, you don't need to throw everything away. You can continue to work on the noisy state. So that's a little fun. We still don't know what to do about that. Another thing is, instead of discarding the state, we can also take the state to do some kind of learning or some state estimation. We are very wasteful the way we wrote the initial protocol. That hopefully can help save a lot of resources, because we can use it in some regime. We have so many states that we discarded, we can almost do the demography out of the discarded states. So that's a little crazy. And extension that we did work on, and we have the result. We have to bring it up. Is to extend the purification problem to general mixed state that has a difference between the maximum and the second largest eigenvalue. That is with Lydia and with Daniel and Pekov and Shidi. Open problems. If I have a mixed signal state, all the purification problems that I told you about will not amplify that mixed signal. It will amplify the biggest eigenvalue. That's always the opposite. So in that case, the only method I know is to modify. We can also try to amplify or try to purify operations. I was given some literature on work on this, but since I was told about some of these work, it was just 2 months ago, so I haven't had time to know what is known about this work. But there are a lot of connections to other areas of other areas of suppression, or principal eigenvalue contribution. We can give it out later on this work, and other learning algorithms and so on. So I really hope to be able to catch up with related work, and this is all I want to say. Thanks.
Any questions?
So the swap test combines information from two states of the same height in a tree. Feels like there would also be information from states at different heights in the tree. Is there any way of leveraging that?
Yes, in fact, in the first version of the paper, we have full analysis on that situation as well. If the noise is different, then you want to be better than the lower noise of the, like there are two copies, you want to beat the better copy. And if you want to use a noisier copy to improve the noise of the better copy, it turns out to be harder. So sometimes you don't actually have an improvement. And the regime when you can have an improvement depends on the dimension. So there is a port when you can have an improvement or not. And that analysis is still in the paper, but we moved it to the appendix.
You're talking about your memory periodically. You said you needed qubits as well as qubits.
Mhm.
Can you say a little more about, I missed why, but can you say a little more about that?
Sure. The plus state that we use to do the swap test is a qubit. It is just a two-dimensional system there. S1 and S2, these two systems, they require d-dimension because we don't get to choose the dimension of the state that we need to purify.
Thanks, Debbie, again.